Hi everyone, we are now into week 5 of ITD 151 and today I'll be covering lecture 6 which is on data preparation part 3. So today we will cover data mashup, integration, mapping, reduction and transformation. And in the second half of today we will also be using a new tool, RapidMiner, to do data preparation. And this tool will also be useful for your subsequent project module ITD 154. So as the name suggests, we have data from multiple sources and then we combine them together. So this is what we refer to as a data mashup. And what we try to do is to create a single new service in a graphical interface such as a dashboard. So this is one good example where you can see that we have different sources of data from web pages, spreadsheets, database, customer management system, and so on. So what do we do in order to integrate them together and provide a dashboard that will allow end users to readily derive and retrieve the information that they wish as and when needed. So when we have data from different sources, normally they come in different formats. So we have to ensure that we integrate them carefully and into a coherent store. So examples are units that are standardized across. So for example, if it's weight, okay, we use kilograms, and if it's height, we use meters and centimeters. So how do we then do integration? So later in our exercise, you'll notice that we'll use RapidMiner to create a column known as ID, and we're going to use ID to do data integration. So which means that if I have two data sources and both has the column ID, I will match ID in source 1 with ID in source 2 and integrate them. So you can see in the example here, customer ID in source A and customer hex in source B. So actually both are referring to the customer ID. So what we need to do is to get the system to recognize that they are the same, and we will use the rename in our exercise so that both carry the same name and can combine together. So when we do integration, we also need to take note of the entity identification problem. For example, former US President Bill Clinton, in some data sources we might capture his name as Bill Clinton, but in other sources we might capture it as William Clinton. And actually his media name is William, and hence his full name is actually Bill William Clinton. So this is what we have to resolve. And another issue that we need to resolve is actually redundancies. So for example, when we have a column known as date of birth and a column known as current date, we do not really need another column, okay, called age, because age can be readily derived, okay, by subtracting from the current date the date of birth. So another example is the Singapore. Our item list price is included a 7% GST. So do we need another attribute for GST amount? The answer is probably no, because from the list price we can readily calculate and derive the GST amount. So one way to actually detect redundancies is to actually perform a correlation analysis. Okay, this is a statistical evaluation method used to show whether and how strongly pairs of variables are related. Strong relation, weak or no relation between two variables. So examples include student results and the amount of time spent on Polymorph. We might probably see some kind of a correlation, okay, whereas if we compare student results versus where they stay, or the student results versus the correlation with the student number, we probably will not see any correlation. So duplication and inconsistencies is very common. An example is a survey where I provided NYP email, and then in another survey I might provide my Gmail account. So but both are actually my emails. In terms of detection and resolution of data value conflicts, so this is a case when we have data from different sources. So for example, in Singapore we capture weight in kilograms, okay, whereas if the source is in UK, the weight will be captured in the unit of pounds. Similarly, for height, different sources may carry may be captured, or may capture the data in different units. So for example, for height in Singapore we use meters and centimeters, whereas in US they might use foot. So when we integrate this data from two different sources, we need to make sure that the unit of measurement are consistent. Okay, if not, we need to do the conversion before we start to analyze the data. So in ETL process, okay, so ETL refers to extraction, transformation, and loading. So in the ETL process, the first step is to map the data between the source systems and the targeted database. So for example, the name captured in the database 1, DB1, is full name, but the analysis I want to perform require me to split the full name into two attributes, first name and last name, in the target database. So why do we need to do reduction? So when you have too much data, this is very practical for your ITD 154 project. Okay, if you have too large data set, alright, your processing speed can be very long, and your processing can be very complex, alright, which result in impractical, it's impractical to analyze such a big data set in the data analysis process. So the idea of reduction is whereby we obtain a reduced representation of the data set and yet retain the integrity of the original data. So for example, the original data is going to show an upward trend, then the reduced data set should also show an upward trend. So what are some of the techniques available for reduction? So we will cover dimensionality reduction and numerosity reduction in the next few slides. There are techniques like wavelet transforms and PCA, which are statistical procedures to reduce the number of attributes. We will not go through them in depth. Alright, so but in this module, instead we will cover techniques like regression, log linear model, histogram, clustering, sampling, and data cube aggregation. So as mentioned, data reduction will help to reduce dataset size, eliminate irrelevant features, and reduce noise, and which makes the smaller data set easier to process and visualize. So wavelet transforms and PCA, they are data mining algorithms. Alright, and so another thing that we would like to share here is that when we do data mining, alright, what we want to do is to be able to identify patterns and establish relationships. So how does data mining works? Alright, there are various analytical software which are available. They use statistical, machine learning, and neural networks approaches. And generally, any of these four types of relationships are being solved. Okay, so we look at the different. We want to have different classes. We want to have different clusters, associations, and also the sequential patterns. So in short, okay, in data mining, what are we looking at is to observe trends, observe patterns, okay, associations that we want to use to aid our future decision making. So in terms of attribute subset, selection, what we mean is that we do not need both set of information at the same time, or an attribute, or we can remove an attribute that is not useful for analysis. So in terms of attribute subset selection, there are a few methods such as stepwise forward selection and stepwise backward elimination. So example of a stepwise forward selection, okay, so this procedure begins with an empty set of attributes, and then we will select among the best, okay, the best among the original attributes to add to the reduced set. Okay, so when we do selection, okay, we need to avoid adding redundant or irrelevant data attributes. So for example, in this case, the student's admin number is irrelevant to the task of predicting students' GPA. So when we want to analyze the factors influencing students' GPA, we will not include the student's admin number. In terms of attribute creation, so you want to create new attributes that can help to capture important information and improve accuracy and better understanding of the data. So for example, when our course manager wants to present student achievements to management, instead of presenting individual test scores, she may want to total up the test scores and present it as a grade. So we have there are three different kinds of strategies, okay, that we can use this. For example, in sentiment analysis, we want to help a business understand the social sentiment of their brand, product, or service while monitoring the online conversations. And there are also domain specific, okay, for sentiment analysis. So for example, crowded, the word crowded, okay, should be given is considered a negative sentiment if it's used in a bus capacity, whereas if it's the same word crowded, okay, might refer to a positive sentiment, okay, if for example we use it to describe a rally in the political domain. So the other one that we are actually looking at, okay, so there are other techniques like mapping data to new space. Fourier transform is an algorithm that converts the data from time domain to frequency domain, and data discretization is used when we want to convert or partition continuous attributes, okay, into different bins. So one way to reduce the data is to fit them to certain models. Alright, so there are methods, okay, that can this model, okay, can then be used to describe the data. So down here we have two different types of methods for modeling the data. One is parametric method, the other one is a non-parametric method. In parametric methods, okay, this involves parameters and the data fits into the models. Okay, in non-parametric, okay, no parameters are involved and there is no model to describe the data. Okay, so why do we want to do this? So for example, if you have so many points, we can actually use a straight line or curve to represent all these points, so that I can even predict the future data points when needed. For non-parametric methods, which does not involve parameters and models, the methods include histograms, clustering, sampling, and data aggregation. So one example is actually the normal distribution that we see over here. Okay. Okay, so the simplest way is to actually um, is to actually be able to fit the data into certain equations. The simplest model that we can have is actually a linear regression, okay, which leads to a straight line, which we can define through the equation y equals to mx plus c, so that we can draw a straight line through the set of points, and that this straight line become the model to represent the points. So another model is a log linear model, where it's a curve. So we also can have equation which forms a curve to represent all these points. So why do we want to do this? Alright, I think in short, okay, we want to be save a storage space. Okay, so imagine when you have when you represent a full set of data points using a straight line, all you need to know is to know the gradient and the y-intercept, and you'll be able to form the straight line that represents all the data points. So all you need is to store the gradient, the y-intercept, and you get the straight line. Okay, so you don't need to store all the data points. And more importantly, when we have a model, we are actually able to use it to predict the future points. So as shared, we want to fit the straight line or curve to represent data points. So how we know is a good fit? So looking at this example, the first diagram represents all the data points, and the second diagram we use a straight line through the points too. But if you notice, the straight line does not pass through all the points. Okay, we draw a straight line through the points, but it does not necessarily pass through all the points. So some of the points are on the left side of the line, and some are on the right side of the line. So in order to measure whether the line is the best fit to represent the data points, there are some techniques, okay, for us to do so. Okay, so we can actually measure the distance between the straight line and the individual points. So we will know that the straight line is a good fit, okay, when the distance between the points and the line is actually minimized. Okay, meaning that the distance between these the straight line and all the points is actually the smallest. Okay, so that is the best fit that we can have. In terms of non-parametric analysis, we have a histogram. Alright, so we can actually in the histogram, what we do is that we actually assign the points, okay, into different range. Alright, so if you look at on the right hand side, okay, from a normal distribution, alright, we can actually assign the points in a normal distribution into a histogram. So you can see from this diagram, each rectangle represents a number of frequencies that lie within that particular class interval. So clustering, as the name suggests, okay, we want to cluster our data, so that what we do is to put the data points that are similar together. So in the example here, you can see 3 clusters: red, green, and blue. So so points that does not belong to any of these clusters will be identified as outliers, and we can remove them. So one of the limitations of clustering is that if you look at this example, there are some points that are not so clear. It's sitting at the border, and so examples of the points here, they can be either belonging to the red or blue. So they are sitting in between the clusters. The last one is data cube aggregation. So what does it mean? So if you look at any one of these cubes, it's actually 3-dimensional. So in this example, each cube consists of information on the time, product, and location. So within one single cube, we can obtain 3 different types of information, and this is what we mean by data cube aggregation. So in terms of histogram analysis, there are two types. One is equal width and the other one is equal frequency. So most common histogram that we use is equal width, which is the one on top, okay, the equal width. So the horizontal axis, you'll notice that the intervals are all the same. So I say again, in an equal width histogram, in the horizontal axis, okay, all their intervals will be the same. Okay, so there's an error in the slide here. If you look below, it should be equal frequency. Okay, the graph at the bottom right hand corner should be equal frequency. So if you look at them, okay, so the width of the interval is actually different, but the frequency is the same for all of them. Okay, so equal frequency means that the frequency is the same throughout. Okay, so histogram in short here is a is a graphical representation of the distribution of the numerical data. So it is an estimate of the probability distribution of a continuous variable. And to construct a histogram, the first step is to bin the range of values. That is to divide the entire range of values into a series of intervals. Cluster analysis or clustering is the task of grouping a set of objects in such a way that objects in the same group called a cluster are more similar in some sense or another to each other than to those in other groups or cluster. So as mentioned, it is effective if the data is well clustered. If we have many points that sits on the border, then the clustering approach may not be too effective. So another way to actually reduce the data is to do sampling. So sampling is concerned with a selection of a representative sample to reflect the characteristics of the entire population. So the key principle is to select a representative subset of the data. So example, in a classroom of 30 students, in which half of the students are male and half of the students are female. So a representative sample might include 6 students, 3 males and 3 females. So the sample we choose has to retain the integrity of the data. So but in random sampling, alright, this may result in a poor performance in the presence of skewed data. So example, the government implemented a new policy. They want to get the view from the ground. If random sampling is used, okay, it might be a case where we have a lot of representatives being Chinese. Okay, so what about the other minority race groups? So in this case, we might want to develop stratified sampling, okay, where we ensure good representation from different race groups. So we have further illustrations on what we mean by stratified sampling in subsequent slides. So there are different types of sampling. Okay, a simple random sampling. Alright, so where for example, in a class of 30 students, every single student has an equal chance of being chosen. Alright, when we use random sampling. So if you want to avoid choosing any member of the population more than once, then you need to do sampling without replacement. And the opposite will be sampling with a replacement, meaning that after choosing any member of the population, okay, we can choose it again. So one example is the 4D and total, okay, so where the numbers selected can be repeated. So stratified sampling, as what was shared earlier, okay, you partition the data set and then we partition, okay, and then we do the sampling. So you partition before you do the sampling in a stratified sampling. So in the example earlier, okay, you can partition according to race, and then we do a sample from each of the partition. Okay, so this is a graphical illustration of what is of sampling with without replacement. Okay, so any number that is being chosen will not be selected again. Okay, and this is an example of a stratified sampling. Okay, so you'll see that we first, okay, divide the populations into different groups called strata, and then we have representatives from each individual groups. So, and it's also recommended that we extract, okay, based on the percentage of each of the different groups within the entire population. So as said earlier, data cube aggregation, okay, it refers to when we means that we store multi-dimensional aggregated information. So you can see from here the original cube has quarter 1, quarter 2, quarter 3 and quarter 4 of sales data. Okay, and we can also have the different states, alright, and the different categories. So so what we see here is that you know, within a cube, okay, we know the time, okay, the quarter per year of the year. We know the location, okay, which is the state, and we also know the different categories. Okay, so these three information are stored within every cube. So data mashup is where the data is transformed, and it can involve the following. Okay, smoothing noisy data, which we covered in data cleaning; attribute constructions, which covers in which involves data reduction; and aggregation, okay, which is the use of data cube aggregation. Next, we're going to cover normalization, data discretization, and concept hierarchy generation for nominal data. So normalization is a very important step when dealing with parameters of different units and scales. So when we normalize data, we convert the data to a range of 0 to 1 or -1 to 1. So there are two common normalization methods. One is the min-max normalization. The other one is z-score nominalization. And we have further examples to illustrate them. So in min-max normalization, it performs a linear transformation on the original data, and at the same time preserve relationships among the original data. So the next slide will have further illustrations. So before I go on to the next slide, this is the formula for the min-max normalization. So based on the formula, okay, shown in the shown over here, okay, 73,600 corresponds to 0.716 on the new min-max range 0 to 1. So instead of using 73,600, we can use the normalized value 0.716 for analysis. For min-max normalization, we need to know the mean and the maximum values. But in the case, if we do not know the minimum and maximum values, okay, there's another approach that we can use, which is called the z-score normalization. So in order to use the z-score normalization, Alright, all we need is to know the mean and the standard deviation values so that we can do the data transformation. So here is an example of a z-score normalization. So using the previous example, okay, so where does 73,600 map to now? So based on the formula for z-score normalization, okay, we plug in the values, the mean and the standard deviation, and after the z-score normalization, the value is 1.225. Alright, so what you observe here is that different normalization techniques will give you different normalized values. So it's when you use the so it's actually important that when you want to do normalization, okay, you apply the same technique on the entire set of data, else you will disturb the accuracy of the data. So discretization, as the name suggests, we convert the continuous data into intervals. Alright, so interval value labels can be used to replace the actual value data values. So discrete data is like a histogram. Okay, we have range and we have frequencies. Alright. Okay. So another example of next we're going to talk about this concept hierarchy. Okay, so this is a good example is where low-level data such as numeric value for attribute age can be replaced by higher level concepts such as young, middle age or senior. Do note that details is lost by such a generalization, but on the other hand it becomes meaningful and easy to interpret. So a concept hierarchy for a given numeric value, numeric attribute, okay, defines the discretization of the attribute. So concept hierarchies can be used to reduce the data, okay, collected, and replace low-level concepts such as numeric value for the attribute age by higher level concepts such as young, middle age or senior. So although details is lost by such generalization, it becomes more meaningful and is easier to interpret. So some reflection questions here. So what are some of the potential problems in the process of data integration? Okay, so what are some of the potential problems that we face in data integration? So there are a few issues, okay, you can find them in slide 6 to slide 8. Okay, so for example, we need to do schema integration, okay, and then there's entity identification issues. We need to remove redundancies, we need to look out for duplications and inconsistencies, okay, and we also need to detect and resolve data values conflicts. Alright, so what are some of the techniques that can be used in data transformation? So data transformation, okay, there are a few ways to do them, and this includes the normalization techniques that we have, okay, min-max normalizations or z-score normalizations. So these are all data transformation techniques. Okay, so with that, I come to the end of lecture 6 on data preparation 3. Alright, so you will have more exposure, okay, on data preparation, okay, and you will do that using a rapid miner.